It's time to add some new ammunition to your integration arsenal in calculus. Let's use a very friendly function, y equals x plus 1. By the way, someone could also just call that function f. Same thing. And it's just minding its own business, doing its thing. And you learned how to do integration. So for example, the integral from 0 to 4 of this function, you can think of it as this shaded area underneath here, which would be a trapezoid, or you could do integration by hand and come up with an answer of 12. That, by the way, that should be the same answer you get if you do the trapezoid, but look at this antiderivative, plug in limits of integration. So what we have there, though, according to this dx, is we have area trapped between this function and the x-axis as we travel from 0 to 4 along the x-axis. So hopefully by now it's kind of instinctive that you just visualize this trapped area. I don't want to draw that in there because then that's going to distort what we're going to do next. But you get the picture, right? Well, now let's take the same scenario, and I'm going to call this function f, and I'm going to write something different. I want to know the integral. Ignore all the rest of this for a moment. I want to know the integral from 1 to 5 of function f with respect to the y-axis. Murmur, this is brand new. This means I need to travel from 1 to 5 along the y-axis, and I need to trap area between the function and the y-axis. That means I travel from 1 to 5, and I'm trapping all of this area. It's a totally different problem than what we did over here. They're not even really related to each other. So this trapped area is a triangle. In this one, the trapped area was a trapezoid. Well, we have a small problem, because if I replace function f with x plus 1, like we had up here, we've just committed a naughty. And the naughty is this. This tells us the variable we're using has to be y, but I've got an x there. So what I need to do is take my equation and rearrange it and solve for x. In this case, that's really easy. Just move the 1 over. Now I get to say x is the same as y minus 1. Oop, I have a mistake, I think. Hold on a second. Okay, I thought about it, and I don't have a mistake. So anyway, instead of making this a y equals equation, I turned it into an x equals equation. So this step above here, which I said was naughty, I ignore it, and I rewrite it. This equation should look, or this integral should look like that, so that I have my equation written with y as the variable. Now the nice thing is, from there, I just go ahead and do integration like I'm used to integration. Antiderivative, limits of integration, plug in my limits of integration, and I get an answer of 8. Which, by the way, makes a lot of sense. You may need to pause it if you need more time to digest that. But my answer was 8 using integration with respect to the y-axis, which makes sense because if I look at this triangle, it's a 4 by 4 triangle for an area of 8. So that's integration with respect to the y-axis, which is, in this case, something very different than if I would have done integration with respect to the x-axis. So now I have a new scenario. It's a little bit more complicated, and I want to find the area trapped between the curve and the y-axis. So here's my curve, here's the y-axis. I want to find that red polka dotted area. So part of the reason of learning integration with respect to the y-axis is knowing that technique will help you save a lot of time and effort on this problem. Because take a look, this polka dotted area is perfectly trapped between this graph and the y-axis. So I can easily do integration with respect to y and get my answer. I go ahead and I take my y equals equation and I solve for x. So now it's an x equals equation. So I really could say, well, yeah, it's y equals x squared minus 4, or it's x equals y plus 4. Same thing. So now I can go do the math. I can't do integration with respect to x-axis because that's just giving me something totally different. It's not what I'm doing here. I could say, all right, well, I need to do integration with respect to the y-axis, which means I go from -4 to 10, and I write the equation. But it's not perfect because I'm writing the equation with x as the variable. In other words, I chose that equation. When I convert it into square root of y plus 4, this thing converts to that thing. Now we have it. That's what you need to do. This will give me the amount of trapped area. If I tried to do this by hand, I could probably get it done, but it's going to take a while. I just want to show you that you could do that same thing via calculator, but it's a little bit tricky. So here's why it's tricky. I want to use this integral in my calculator, but notice it's using y as a variable. Well, calculator doesn't care what variable you're using, so I use x. Instead of square root of y plus 4, I do square root of x plus 4. Because remember, if this was a t, if this was a v, if this was a w, calculator doesn't care, it just uses x. So there's no problem mixing up the y with the x. So now I would go second calc, and option 7, I would integrate. Now as you're doing that, you might be concerned, I'm going to go from -4 to 10, you might be concerned because the graph doesn't look like the graph we're working with. Well, you just have to get over it because we've done some changing of the equation and so on and rearranging. So this really is the answer, 34.922. But you just have to trust that the picture you're seeing does not necessarily match the picture you're working with. But the answer's still right. So this is integration with respect to the y-axis. In this case, it bailed you out because doing this problem with integration with respect to the x-axis would have been a real doozy, and we'll talk about that when we do the trapped area segment. See ya.